Let's examine the units of the velocity vector in polar coordinates. We're going to perform some dimensional analysis. We're going to make sure that all the terms in this expression have the same units. So we want consistent dimensions. So let's go ahead and write down the expression. First, on the left-hand side, I'm going to write down v, and v is a vector quantity, so I'm going to put a little arrow on top, and this is the velocity vector v. And I'm going to express it in two-dimensional polar coordinates. So for now, we're just dealing with two dimensions. We're in this plane over here. We're in the plane of the whiteboard. So we're going to have two components. We're going to have one component that is in the tangential direction and one in the radial direction. I'm going to write the radial direction first. So first we have r dot times r hat. So r hat is the radial unit vector. It's the unit vector that always points in the radial direction. And this over here, this is r dot. That is the time derivative of the radial distance away from the origin. So this over here, this is a scalar quantity. And this scalar quantity is scaling a vector quantity. But this vector is a unit vector. So it's a special type of vector that has unit length. And that's why I've put a little hat on top. These guys are the basis vectors that we're using to construct every possible vector. Now, this is just the radial component. Let's write down the tangential component as well. We're going to have a tangential component, and that tangential component is going to have r times theta dot in the theta hat direction. So theta hat over here is a unit vector. This is the unit vector for the tangential direction. So this guy points along the radial direction, and this guy points along the tangential direction. And together, we can use them to construct any vector. And this vector over here is the velocity vector. Over here we have theta dot, which is the time derivative of the angle, and then we're multiplying by r. And r is the radial distance. So these guys are both scalar quantities. So we have scalar quantities multiplying unit vectors, and those are being added together, and that's giving us the velocity vector. So let's examine the units of each of these terms and make sure this is all consistent. So let's have a look at this one over here. What are the units of velocity? Well, in the last video in this playlist, we actually discussed the units for position, velocity, and acceleration. And we found that when we take the time derivative of position, we actually get a unit of time. We're dividing by a unit of time. So position, which is in units of length, turns into length per unit time. That is the units of velocity. So let's write that down. We have length per unit time, which is length times time to the -1. So length per unit time. And that is the general way of writing it down. So this is length and this is time. But if we want to write it down in SI units, it would be meters per second. So that is the units of velocity in SI units. So now let's have a look at these two terms. What is going on in this term over here? Well, r, the radial distance, that has units of length. But we're taking r dot over here. And this dot notation means that we're taking the time derivative. So we're doing the same thing that I just described for velocity. We're taking a length and we're dividing it by a unit of time. That's what happens when you take the time derivative. So this term over here is also going to have length times time to the -1. It's going to be length per unit time. So this is dimensionally consistent. Now let's go to a slightly more difficult case over here. We have r times theta dot. This r has units of length. It's a length. It's a radial distance. So we do have an L. But what's going on with this theta dot over here? How would you define the units for theta dot? This is the time derivative of the angle. So the angle is usually measured in radians. Radians are a natural unit to measure the angle with. And when you take the time derivative, you're again dividing by a unit of time, because you're dividing by a little infinitesimal delta t, and then you're taking the limit as delta t goes to 0. That's what you do in the process of differentiation. It's one of those core concepts in calculus, differentiation. So this over here is going to be radians per unit time. But radians, we can actually just ignore the units of radians. We can just treat that as a scalar that is multiplying other quantities. So this we can treat as just having units of per time. So per time. You can think of it as cycles per second, but you're going to have to introduce factors of 2 pi in places. And that is how you link the angular velocity to the frequency. And those are things like frequency and angular velocity that are used in describing rotations and oscillations. So that is actually a very important distinction that we have to make. We have to keep in mind that when we are actually doing computations with this, we're dealing with radians per unit time. But if we're looking at this as a collection over here, this is a collection of terms being multiplied together. It's going to get a length and then a per unit time over here. So we're going to get length per unit time if we take both of these guys together. So you can pretend that radians don't actually have units. Even though when we're actually doing a computation, we will be measuring the radians in terms of a chunk of the circle, right? It's a chunk of the unit circle. So we can see that both of these terms have the same units. So this is dimensionally consistent. We've performed dimensional analysis and all of the terms match their units. And this is very important. If you have things that you're adding together in an equation, all of the units have to match. Otherwise, it doesn't make physical sense to add those things together. So when you multiply things together, the units multiply as well. So you get that length over here, and you get that per unit time from this one over here. So you can see that if you have just a time derivative of a length, then you're going to get velocity. But if you have just a time derivative of an angle, you don't have the units of velocity. So you have to scale that by something that has units of length. So you need something with units of length and something with units per time to multiply together, and that's going to give you velocity. So this is the velocity vector written in 2D polar coordinates, and we've checked that all of the angles make sense. So one final little thing over here, I'm just going to write, just to make this very, very clear, this you can think of as radians per unit time. And when we're multiplying radians per unit time by something that has length, we're just going to treat that as length per unit time. So we're going to treat that exactly the same as we would a velocity. So we have an angle per unit time, and we're multiplying by a unit of length over here. And this is often referred to as radians per second. That's the SI unit system. So radians per second is what this is actually going to be measured in. So if you're physically measuring theta dot when you're doing an experiment, you're going to measure it with radians per second. You could also use degrees, but degrees are a lot less convenient and they're a lot more arbitrary. That's why we prefer to use radians. So I hope this video was helpful. In the next video, we're going to have a look at all of the terms in the acceleration vector. And we're going to have to make sure that all of those terms are dimensionally consistent. We want to make sure all of those terms that we're adding together have the same units. You can find that video in the quantum mechanics playlist if you click over here.